Okay, so today what we're going to talk about is sets. Oh, sorry, not sets. We talked about sets last week. Today we're going to talk about function and just maybe a couple simple stuff about functions. Just stating the definition, right? But when you see a definition, it's not just about stating it and then knowing some example. It's good to know some non-example, right? Something that doesn't satisfy the definition. So I'll go over counterexample too. And the second thing that I want to focus on is the image of a function. And people always say image of a function. They also say range. They also say codomain. And there's a lot of different words there. So I want to go over what are those words. Is everyone ready to start? So, okay. So I think to start off, instead of just showing you definition of function, I hope you read the book, because I'll give a little poll question on the definition of a function instead. So 1 second. Okay, so the definition of a function, let me put up the poll. Okay, so which of the following statements defines, represents the definition of a function? So for each y, there exists x such that f of x equals y. B is for each x, there exists a y such that f of x equals y. There exists x such that for all y, f of x equals y. There exists y such that for all x, f of x equals y. Which of the following is the definition? I'm looking for the definition of a function. I guess I wrote that down already. But I want to emphasize what I'm looking for is the definition. Okay, you can select no answers, by the way. Selecting none of them may or may be valid, may or may not be valid. Now people are getting worried. Okay, I'll give you another minute. Thanks, man. Thanks. I'll give you another minute. Okay, the definition of a function. What is a function exactly? Okay, almost everyone's voted. I'm going to give 20 more seconds. Ten more seconds. Okay, a lot of people are saying B. Okay, so here's the result of the poll. Almost everybody's saying B. Some people saying A, some people saying Y. Oh, sorry, C and D. But mostly people are saying B, right? Let me give you, okay. So B is very close to the answer, but B isn't actually quite right. Does anybody know why? Does anybody know why, how I can make B a bit more precise? To be honest, I don't know if I did that on purpose. I think I phrased the thing incorrectly in a way that, or let's just say I did it on purpose. Does anybody want to point out what's wrong with B? Chat is moving slow. People are not sure. Oh, okay. Excellent. Good. Unique. Exactly. B isn't quite right. Actually, none of these really reflect the definition of a function. I can explain why. But the correct definition would be something like this. For each x, there exists a unique y. That's the keyword, unique. Y such that f of x equals y. And the reason it has to be unique is because for each input, the function has to give only one output. So if it gives more than one output, then that doesn't count as a function. So let me give you some example. Okay. Here's a simple example. Maybe I'll just take the function f, whose domain is the natural numbers, and the codomain is also the natural numbers. So this first thing here represents the domain, and this represents the codomain. Codomain, the difference is just maybe you can think of the domain as the set of inputs, and the codomain as the set of some set of outputs. But I think we're going to talk about range in a second, and range and image, and those are a little bit more subtle. But let's just say like this, and here's an example. Let's say f of n equals 3n plus 1, right? Completely unambiguous rule, because I can say, for example, that f of, I don't know, 6 would be 3 times 6 plus 1, which would be 18 plus 1, so 19, right? You can, given an input, you can say some unambiguous output. Okay, so that is, I mean, this isn't surprising at all that that's a function, but let me give you an example of something that looks like a function, but isn't, because this uniqueness bit fails. So here's an example. Let's say g is a function from q to, let's say, z, the integers. Remember, q is the set of rational numbers. Remember, q is the set of all rational numbers, a over b, where a and b are integers, and b is non-zero because it's in the denominator. And remember, z is just a set of integers. So we write 0, plus minus 1, plus minus 2, and so on. Okay. Hey, people talking about domain and codomain. Good. I will show you, I will explain image in a second. We're going to go over that a lot today. Here's the function that I want to give you. Okay, so I'm saying g is a function from q to z. That means that it takes as an input some rational number, and as an output, it gives some integer. So let's write it like that. Sorry, I called it g. G of some rational number a over b. Let's just say it returns the denominator, b. So it takes a over b and returns b. So for example, I could plug in, I don't know, g equals a g of 2 over 3. That would be 3 because that's the denominator, right? Any questions about this example here? There should be a question. There should be a big question about this example. Okay. What about 0? Good. No, I don't agree with that. 0 is fine because g of 0 would be, well, I can write 0 as 0 over 1. And so I give the denominator as 1. What is the graph? Yeah, it's hard to plot. If you mean the graph by plotting the function, I feel like that would be you can't always plot functions. In this case, when the domain is q, I don't think it's easy to plot it. There's also 0 over 2. I think somebody's getting to it. B can't be 0. Yeah, 4 over 6. Excellent. Okay, I think people are getting to it. There's some ambiguity. Okay, let me just be clear, and you should write this down. This is not a function. It looks like a function. And the reason is that the way it's defined is ambiguous. What that means, and good, people are getting to it now. The way I calculated g of 2 over 3, there's another way to do it. I could have said g of 4 over 6. That's exactly the same, right? And 4 over 6, that the denominator there is 6. And see, I got a different output on the same input. The input looks different, but it is the same. 2 over 3 equals 4 over 6, right? So on the same input, I got a different output. So you can follow it along, and it looks like I'm saying 3 equals 6, which is complete nonsense, right? This function is completely ambiguous. There's more than one answer given a single input. So that ambiguity means that the function is not well defined. It's not even a function. It's a relation, but it's not a function. Okay, people, does that make sense? I can give you a little bit of a visual for that, because let me name these examples. Let's call this first one A, or whatever. They're already called F and G, so that's fine. Here's a little visual. That function from n to n, here's the example A. Here's the set of all natural numbers, and here's another copy of the set of all natural numbers. And f is supposed to be a function that goes between them, right? The way I've defined this f up here. So in this example, I made f to be 3n plus 1. F of n is 3n plus 1. So for example, if I plug in 1, I'm going to get the output as 3 times 1 plus 1, which is 4. So if I apply f, it moves 1 over to 4. Okay? And as another example, if I plug in 6, I'm going to get 3 times 6 plus 1, which is 19. Okay? So this is just how f works. You can see that each element of the domain maps over to exactly one element of the codomain. And there's a lot of numbers in the codomain, right? Like, I don't think there's any number where 3n plus 1 equals 5. Right here, okay. Let me make this a bit more concrete. Let's just do all the numbers. 1, 2, 3, 4, and 5. Let's do all of those. And let's write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just write a lot there. Now 3n plus 1 would be 4. So 1 maps to 4. 2 times 3 plus 1 would be 7. So 2 maps to 7. 3 times 3 plus 1 equals 10. So 3 maps to 10. And then 4 and 5 map to things that aren't, I wasn't able to list out. But you get the idea. The point is that each element here maps to some element here, and only one. Now let me give you the other example. B. Here's the set of rational numbers. So maybe I'll put a 0, 1, 2, 3 in it, but also a half. Also, I don't know, 3/4. Also, 4/3. No, yeah, sure, that's fine. And here's the set of integers. 1, 2, 3, 4, 5, and so on. Now, notice that, so let's take my function g here. Notice that a half maps to 2 under my function g, right? This is the function g that I have here. People following along? I can't tell if anyone's following along. Okay, good. Yeah, so this function here, it'll send 1/2 to 2, but it'll also send 1/2. I can also write 1/2 as 2 over 4, and that would map over to 4 because it would pull out the denominator, right? So for example, 1/2 would also map to 4. And the reason this isn't a function is one input has 2 outputs. That's the whole point. In fact, it has more than 2 outputs. I could also have written it as 3 over, I could have written 1/2 as 3 over 6, and then it would have mapped to 6. Each input has infinitely many possible outputs, and that's not what a function is. Okay? It takes one value and it gives you out many. Exactly, 1 goes to many. In this case, 1 goes to 1. So that's called a 1-to-1 function. We'll talk about more later. Okay. Now, one thing you'll notice here is that in this example, this number 1, okay, here, look at this number 3 here. Is there any way that there's any value I could have started with, any input value that maps over to 3? No, right? Because I only get multiples of 3 plus 1, right? I only get multiples of 3 plus 1, and 3 is a multiple of 3 plus 0. So, yeah, so I should have said this is n maps to 3n plus 1, and this function was a over b maps to b, which was not well defined. Okay. All right, so not every number in this codomain, by the way, yes, this is the codomain. Not every number in the codomain is associated to some input. So that means that this number is not in the range or the image. So that's the terminology we use. So let me define the image of a function. If f is a function, let's say from x to y, oops, and I have well, let's say if f is a function, let's say, and a is a subset of x, that we define the image of a, let's say the image of a under f, to be, and there's really there's one definition, but you can interpret it in two ways. Let me show you. So it's the set of all possible outputs where the inputs come from A. So it's the set of all possible f of a's where A comes only from our subset A, capital A. Another way to say it is it's the set of all possible outputs y, so y and y, such that there exists an element A in capital A such that f of A equals y. So this is the set of outputs that's achievable by some input from A, okay? And since this is a set of elements of y, this is a subset of capital Y, okay? Okay, so this is what the image of a function is. Let me give you an example. Oh, actually, I'll give you another piece of terminology for the example. This is the image of some set A, just some random subset of X. But I can take the image of all of X, right? And if I do that, I get something called the range. So that's f of x, f of capital X, which is the set of all outputs f of x, such that x is an element of x, capital X, a lot of x's. So image and range are different. If I say the image of A, that's one thing. If I just say the image of F, usually that means range. So that's a word quirk of the terminology. Image of A, of a set A, that refers to f of A. If I say image of F, I didn't specify A. So what mathematicians mean when they say that is they mean all of X. So image of F would be the same as the range of F, which is the same as just f of capital X, okay? So the image of a set is different from the image of a function, okay? This you can think of as the image of A under F if you want, but you can see how the terminology is slightly different, but at least it's unambiguous. That's the point, okay? So, okay, so let me give you some examples. Let's go back to our good friend from earlier, f from the natural numbers to the natural numbers, and let's just say 3n plus 1. F of n equals 3n plus 1, right? Let's calculate the image of this set, I don't know, 3, 4, and I don't know, 8. Image of this set under F. All I have to do is take, well, let's write it out. F of this set means I just take the set of F applied to each one of these values. That's basically all I do to find the image of a set. And so this would be f of 3, f of 4, and f of 8. That's what the image of this set is. That's it. That's all I have to do is plug in these numbers. So I would get, oh, and I have another poll question for you, but that'll be later. Move it out of the way. Okay, and so I can actually calculate each one of these numbers. F of 3 was 10, I guess. 10. F of 4 was 3 times 4 is 12 plus 1 is 13. 8 times 3 is 24 plus 1 is 25. Okay, makes sense? That's all I have to do to calculate the image of the set. But how about the image of the entire function f? So for this, I need to look at the set of all possible outputs. So I need to look at f of the set of all natural numbers would be 3n plus, well, you can write it like this, f of n as n ranges through every possible natural number. And I can just write that as the set of 3n plus 1s, because that's the definition of f, as n ranges through the natural numbers. And at this point, it's just an infinite set. So either I can leave it like this in set builder notation. There's not really many ways I can simplify it. Or I can try to write out some of the elements. So when n is 1, 3 times 1 plus 1 is 4. When n is 2, 3 times 2 plus 1 is 7. And then, oh, sorry. And then it just looks like there's a pattern. I just keep adding 3. So once you identify a pattern, you can just put dot, dot, dot. And maybe, hopefully, whoever's reading this finds it clear. Okay, so you can see the difference that, so the way I would define or say in words is that codomain, here, let me say something because it can be confusing. Codomain is the set of possible outputs, set of all possible outputs. And you don't know which outputs are actually achievable though. Those are the image. The image or range, let's say, this is the set of all achievable outputs. This is what I would say the difference is. And you might think the difference is kind of unclear there, but the point is that in this case, in this example here, the codomain was all natural numbers, right? In this case, the codomain was all natural numbers. And the domain was also all natural numbers. But not every natural number can be reached. For example, I can't reach 5. I can only reach 4, 7, 10, 13, 16, and so on. So the only numbers that the function can actually output, those are the range. So the numbers that are among the possible candidates for all the possible outputs, the candidates for the values that f outputs, those are called the range, okay? So here's another example. I'll give you a slightly more complicated example. Let's say a function g from the real numbers to the real numbers that takes a number x and gives me something like 3 minus 2x. Okay, this is a pretty simple example. So what I want to do is find g of, say, some interval -1 to 4. Okay, let's try this problem. So the way I approach it is I write out the definition of the, so yeah, I start with the definition of the image. So g of -1 to 4 would be the set of all possible values g of x, where x is in the interval from -1 to 4, so which I can write as x is between, I can use inequalities to represent that interval. Okay, so this is the definition of the image. And I wanted to ask you something about my problem in a second, but I'm going to keep making more space for myself. This is the definition of the image of a function. And now let's say, okay, so what I need to do is figure out all the possible outputs. So let's draw a picture just to help. You probably know that this function is a line, and the y-intercept is here at 0, 3, and then it has a slope of 2, right? So let's draw that. I think I got it. There. This is the line y equals 3 minus 2x, right? And what I want to look at is what possible values can this function achieve between -1 and 4. So in this interval, what can the function achieve? Well, since this function is a straight line going down, I can look at what's the biggest value it achieves. That'd be over here. This is like the max value. And what's the smallest value? That would be over here at the end. That's the min value. And for this particular function, since it's going down like that, I can look at what possible values are achievable. Anything between here and all the way down here. These are all the achievable values of the function on this interval. And so you might guess, oh, well, this is, how many is that? 1, 2, 3, 4, 5. So -5. And then, oh, also 5. 1, 2, 3, 4, 5. So also 5 here. So you might make a guess. And just based on the diagram, you might guess that the range or the image of this function on this domain is the interval from -5 to 5. Okay, so you might guess this, but that's not a proof, right? The proof, to prove that two sets are equal, I have to prove that one's a subset, that A is a subset of B and B is a subset of A, right? So I have to prove these two things. Okay, so let's see what's going on. I know that X is between -1 and 4. So let's try writing something down like that. And this is still maybe rough work, right? And then what I want to do is get a range or a possible output for g of x. And I think it's -5 to 5, but let's try. Well, if I want to get g of x, I'd better manipulate this inequality until it becomes something like 3 minus 2x, right? So what I'll do, my first step is I'll multiply this inequality by -2. So -1 is less, or sorry, -2. So +2 is less than or equal to -2x is less than or equal to -8. Anybody see what I did? Yes, the signs changed. Good. I was seeing if you're following along. When you multiply by -2, the sign switches. And then I add 3. So I see that 5 is between 3 minus 2x, and then -8 plus 3 is also -5. So I can see that 3 minus 2x, which is the same as g of x, is in the interval from -5 to 5. So I think I can say something a little bit here. I can say I've proven that g of x is between -5 and 5. Okay, interesting. So that's my next poll question for you is, what exactly did I just prove? Just based on this work, what can you tell exactly what I just proved? And here, I'm going to start the poll. Nope. There's the poll. Yeah. I'll give you 2 minutes. What exactly did I just prove? What did this whole calculation, this is kind of rough work, what did that prove exactly? Of these 4 statements here. I started with x in this interval, and I just did some logical calculations until I got to this conclusion, that g of x is in this interval. What does that exactly prove? Let's see, how's the poll going? Okay, I'll give you another 30 seconds. There's, I'm still waiting on like 40 people to answer. Ooh, people are split. Okay, 20 more seconds. Almost there. 88% of the class has voted. 10 more seconds. Okay. All right. So let's see the results. Most people said A. 60% of the class said A. A lot of people said B, said C as well. Well, look what I did, right? My process was I started with this assumption that x is between -1 and 4. and I did some logical steps, let's write it like this, until I reached the conclusion that g of x is in negative 5 to 5, right? So basically this shows that any element in this set here, and the elements of this set are all the possible g of x's where x is in this interval. So what this shows is that when x is in this interval, the output has to be between negative 5 and 5. So the answer is actually what is A, which was the majority answer. But does anybody, yeah, so okay, very few people guessed the other answers. This shows that if I start, so this is my end kind of, right? So this shows that if I start here in this interval, then the output is in this interval. And so that means, so this inclusion would have been the other direction, that if I start in between negative 5 and 5, then I can get in between this interval. So, okay, B and C, sorry, B and D aren't quite right. But can anybody make an argument for C? Because C is, I wouldn't say that was the right answer, but there is a little bit of an argument. You might want to say, yes. For correction, yes. C, I see. Yeah, B is true. B is actually true. It's a true statement. Like, yeah, but it's not what I just proved. I didn't think of that point of confusion. Yeah, this is not what I just proved. It is true though. Yeah, B is true. It's just not what I proved. But does anybody want to make an argument? Well, I asked, does anybody want to make an argument for C? And somebody said you have to prove it both ways for them to be equal. That's true. That's why the answer isn't C. But somebody said something earlier I saw. Yeah, Ortiza says, would you be able to reverse engineer from g of x to negative 1 to 4? Yes, I can reverse engineer it. So while the way I wrote up my work didn't prove C, I can use the same work to also prove C. So we can conclude that g of negative 1 to 4 is contained in negative 5 to 5. Okay. Now let's try the other way. Let's try to prove that the other direction, that negative 5 to 5 is contained in g of negative 1 to 4. Okay, and I have to make some more room here. Okay, so let's try to prove it. So to do that, you have to take an element of this thing, of the smaller set, and prove that it's also an element of the bigger set. So let's try that. Let x be an element from negative 5 to 5. Then all you have to do is reach, what you have to do is reach here. So we want to prove that x is also in the image of g from negative 1 to 4, right? And so what does that mean? It means i.e. want to find some value, I called it x. Let's just say some a between negative 1 to 4 such that g of a equals x. I should have called that y, really, not x. Okay, this is what I want. And so I can solve for a, basically, right? That would be, so I can solve for a, and that maybe I'll do on the side. So if g of a equals x, that means 3 minus 2a equals x. And I can solve for a, I get x 3 minus x over 2, right? So this is side work. But now when I write up the proof, let's say let a equals 3 minus x over 2, right? And all I have to do is check that a is in this range, is in this domain, basically. So let's check. Then a is between negative 1 and 4 because, okay, running out of time, I wanted to give you a problem to work on. A is between negative 1 to 4 because, well, let's see. I know x is between 5 and -5. Let's multiply by -1. So 5 is greater than -x is greater than or equal to -5. Let's add 3. So I have 8 is less than or equal is greater than or equal to 3 minus x is greater than or equal to -2. And then I divide by 2. So 4 is greater than or equal to 3 minus x is greater than or equal to -1. And this is the same as this 3 minus x over 2 is just a. So this proves that a is between, well, I'll write the inequalities the other way. A is between -1 and 4, right? And so we say, therefore, A is between -1 and 4. And now I can say, and clearly, if you want to do the calculation, you can. G of A equals 2 minus 3 times A, which is 3 minus x over 2. And you do the calculation, and you get x. So we did it. We did it. We showed that given an element of this interval, that's not what we showed. We showed that given, yes, an element of this interval, there exists some a in this interval, -1 to 4, so that g of a equals x. So we conclude that x is in the image of -1 to 4. And the other direction we'd done earlier, but I didn't write it up in a good proof like this, but I wrote it up in a big mess, and maybe I'll leave it to you to write up the proof the way I did for the other direction. Okay, was that clear, people? Does everybody understand how I proved that? So this is also an example of proving equality. This was an example of how you can prove that A equals B by proving that A is a subset of B and B is a subset of A. And so this is what I did in this example. I proved that, so in this example, I proved that this image is a subset of this interval from -5 to 5. And then I also proved that this interval from -5 to 5 is a subset of this image. So I did two examples at once. Images and set inclusions. So I've only answered half the question. In a sense, I've only answered half the question because I've only written up the proof for one of them. But the other one, the math was all there. I just didn't write it up nicely. So in a sense, I have half the write-up here and half the rough work here. And I want to leave it to you. Oh, what's wrong with my screen? Sorry, guys. One sec. Uh-oh. Uh-oh, something's wrong with my screen. Oh, 1 second. I have to stop sharing for a second. Something's going wrong. Sorry, 1 second. I don't know what happened. Okay, maybe that'll do it. No, still busted. Something's wrong with my screen. Oh, there, it's better. I don't know what that was about. Sorry, my point that I was trying to make, people were saying that what I've done is here's the proof, half the proof. Maybe I'll write that down. In this yellow box is a proof that that the image of the interval is contained in this interval from -5 to 5. Okay, and it's basically all the setup for the proof, but you should write up that proof in a good copy. Now for the other direction, for the other inclusion here it is. I did prove it properly. So you can use this as a template for your proof. Make sense? Okay, a couple people said yes. Okay, it might take some studying before you understand this completely, but at least write it down. Let me give you one example to end off the class. I'll give you 5 minutes to work on this example here. Here's another function. This is a function from the natural numbers to z, and it's defined by some weird formula, -1 to the power n times n. What is the image of all natural numbers? And since it's the image of all natural numbers, this is like basically the range of f. okay? So, okay, class time's almost over. I'll give you 5 minutes to work on this problem and then I'll take it up, okay? 5 minutes to work on this problem. You have to find all achievable outputs of this function. So I'll take it up at 9:57 to give myself a couple minutes. One second. So, okay, so let me give an example. Yeah, this is -1 to the n times n. Okay, just to be clear. Let me give you an example. If I give you f of, I don't want to give it away too much. If I give you f of -10, that would be negative, oh, sorry, -10 isn't a valid input. I'm only allowing natural numbers. So if I give you f of +10, let's say then, this would be -1 to the power 10 times 10. And -1 to the power 10 is 1. So this is just 10. Does that make sense? Yep, don't give, yeah, okay, yeah. Okay, so your goal was to find the range of this function. If you have any questions, feel free to put them in the chat, or you can turn on your mic and you can just ask me. If you're stuck, I'll take it up in 2 minutes. Okay, let's take this up. Any now you can put the answer in the chat if you want to share what you got. Okay, only got 2 answers here. One thing you can do to, yeah. Yeah, yes. So basically you have to do something similar. What did I do for the example above, right? For the example I just did, the first thing I did was draw a graph, right? Now this function that the example, the problem that we just did doesn't really have a graph to it, but maybe we can do something else. This was just rough work. Maybe you should just do some playing around until I make a guess, basically. Does that make sense? The first thing I did was guess, and a mathematical word for guess is conjecture. I made the conjecture and then I proved it. And the way I proved it was by double inclusion. That's just because that's the way we prove that two sets are equal. It's by double inclusion. So let's try that. Let's try making a guess. And in this case, the only way I can really get a handle for what this function is doing is maybe do some more examples. So f of 10 was 10. Maybe f of 3, well, maybe f of 3, let's try that. Let's see what happens. Well, maybe, you know what, let's just start finding all the numbers in order. So f of 1 would be negative 1 to the power 1 times 1, which is negative 1. F of 2 would be negative 1 to the power 2 times 2, which is positive 2. Okay, so I'm already getting an idea, right? F of 3 would be negative 1 to the power 3 times 3, which is just negative 3. And the pattern I'm seeing is that this term here, this negative 1 to the power n, negative 1 to the power 2, negative 1 to the power 3, it's going to be just plus or minus 1, depending on whether I'm even or odd, right? So I can see that even gives a positive answer, and odd gives negative answer. And then I want to ask myself, okay, maybe I ask myself, is f of n equals negative 2 possible? So does that just means, is negative 2 in the range, right? i.e., is negative 2 in the range? Well, basically I would say, okay, this would be negative. This is like saying, well then, yeah, okay. You could try to calculate it, but you can also just notice that, wait a second, no, it's not possible, right? Because for odd numbers, I always get a negative odd output. For even numbers, I always get a positive even output. So now I'm saying, oh, okay, I can see a pattern. And so maybe let's make a guess now. So that's kind of my process for these, whether by graphing, whether by doing examples, I try to come up with what I think is the answer. So let's guess. Maybe the f of n is going to be the set of all even integers, 2, 4, 6, 8, and so on. And in the odd case, so I use union for or. In the odd case, it's negative 1, negative 3, negative 5, negative 7, and so on. Okay? So this is my guess for the answer, okay? And I think I'm out of time. So what I'll do is I'll prove this. Let's do this next time. But why don't you try it on your own? And yeah, definitely try to prove this equality. Try to prove this on your own. And then I'll take it up at the beginning of next class. So we'll prove next time. Okay, people? Let's take this up next time. Okay, then I think that's it for today's class. Take care. I'll see you on Wednesday, but don't forget about my office hours on Tuesday. Okay, bye.